Hello everyone. In this video we're going to take a look at an example of a problem dealing with stoichiometry of gases. Remember, when we talk about stoichiometry of gases, it's the same thing as any other stoichiometry problem that we've looked at so far this year, but we also have two additional pieces of information that we can work with, and we'll see how those come into play in the two parts of the problem that's shown here. So we have C3H4 being combusted at STP, or standard temperature and pressure, and we were told that 5.6 liters of C3H4 are consumed, and we were given the balanced equation for this reaction. And we're asked to find the number of liters of carbon dioxide produced and the number of grams of water produced. The first thing that stoichiometry of gases allows us to use that's different from the stoichiometry problems we've done up to this point is that we also have information about how volumes of various reactants and products are related to each other. So the conversion between volume of one substance and volume of another substance in the reaction is exactly the same as the mole ratio. We get it from using the coefficients in the chemical equation. So in part A, where we're looking to find how many liters of carbon dioxide are produced, we know that we consumed 5.6 liters of C3H4, so we need liters of C3H4 on bottom to cancel out, and we're looking to convert into liters of CO2. And again, the conversion between volumes of two reactants or products in the reaction is exactly the same as the ratio of the numbers of moles of those two substances. So looking at our equation, C3H4 has a coefficient of 1, CO2 has a coefficient of 3. Our units cancel for the liters of C3H4, and so we just get 5.6 times 3. Just like when we're talking about a mole ratio, remember that those coefficients effectively have infinite significant figures, so the only thing limiting the number of significant figures in our answer here is the significant figures in the volume that we started with. We have two significant figures there, so we need to have two significant figures in our final answer, which means that we have 17 liters of CO2 produced. In part B, we're asked for the number of grams of water produced. We could do the same thing that we did in part A in terms of trying to go from what we know about C3H4 to try to learn something about H2O, converting from liters to liters. However, we don't know how to relate grams of water to liters of water. So here we need to do the same thing that we've done before when we're trying to go from grams to grams, say, or moles to grams. We need to get into moles first so we can go moles to compare the two substances. So starting with 5.6 liters of C3H4, we want to first convert that into moles of C3H4. And the key thing here is that we're told that this reaction is taking place at standard temperature and pressure, or STP. For any gas at STP, it is 22.4 liters for 1 mole of that gas. And so being at STP allows us to convert from volume to number of moles of C3H4. From here we will proceed the way we always have in a stoichiometry problem. We have moles of one material, we're trying to get grams of another, so we do a mole to mole conversion first. So we put moles of C3H4 on bottom to cancel out, moles of H2O on top. Looking at the equation, we have a coefficient of 1 for C3H4, a coefficient of 2 for H2O. So we've now converted into moles of water, and now we can use the periodic table to convert from moles of water to grams of water. Remember that you add up the atomic masses, or I should say molar masses of all the atoms in the compound. using the periodic table. So here we have 2 hydrogens, each of which is 1.01 grams per mole, plus 1 oxygen, which is 16.00 grams per mole. That gives us a total of 18.02 grams of H2O for 1 mole of H2O. And so then we would multiply this out. We are now in the units that we want, grams of H2O. And again, we're limited to 2 significant figures in our answer, and we will end up with a result of 9.0 grams of H2O. So to review, the things to keep in mind when we're doing stoichiometry of gases problems. The ratio of volumes of 2 substances is the same as the ratio of moles of the 2 substances. And in either case, we figure out that ratio using the coefficients in the equation. If a particular gas is at STP, then 22.4 liters of the gas corresponds to 1 mole of the gas. And so we would have then this conversion factor that we used up here. Whenever we're talking about a gas at STP, we know how to convert between liters and moles. And finally, if what we are looking for in the end is a mass, we do need to get into moles first. Just going liters to liters isn't going to help, because without the density of the material being given to us, we can't convert between grams and liters directly. And then once we have moles, we get to grams the same way we always have, using the periodic table to figure out the molar mass.